Hello friends and good morning. Welcome to all of you for this video lecture on the course Metal Forming and Tool Design 16ME62 subject code. We are trying to cover all those topics which have not been taught in the regular classes. Before we start with the subject, I just hope it has been okay with you. Now, under these unprecedented times, we all need to be focusing first on the health and other healthy activities. So, I suggest to all of you that you engage in regular physical activity and also try to access to the material, videos or any other material, and you try to make yourself up to the mark. You make sure that you have learned the things. Okay, I'm using this file, the Word file. I have a PDF file to share with you. About the course MFTD 16ME62. It's about Unit 2 we are discussing. Unit 2 broadly consists of forging, rolling and RF. Forging has been covered in almost all the divisions. Rolling will be discussed by another faculty, Dr. Nikhil, later in the week. I am going to cover HERF topic for you in these two lectures on today and tomorrow. So HERF stands for High Energy Rate Forming Processes. The rate of strain is a very important factor in metalworking processes. The rate of strain implies the rate at which the deformation is taking place. The plastic deformation taking place or the amount of plastic deformation taking place per unit time is what is the rate of strain. Okay. Now, the rate of strain has very vital effect. The first is the flow stress increases with strain rate, and also because of high rates of strain, the temperature is increased due to adiabatic heating. A quick and a rapid deformation will produce adiabatic heating. At the same time, improved lubrication. And a strange observation is that many of the materials like tungsten and titanium, which are difficult to deform under usual or normal rates of strain, they can be deformed under high rates of strain. And the main principle of HERF processes important features, if you look at, the application of energy is very rapid. So, higher in a very, very short interval of time, and due to which high particle velocities are attained, and as a result It is also called HVF process or high velocity forming process. And very large parts can be easily deformed in very less time. So these are some of the features of HARF processes or high energy rate forming processes. The yield stress and flow stress at low plastic strains are more dependent on strain rate than the tensile strength. So it is one feature. Okay, and the yield point appears for many of the brittle materials like low carbon steels. A ductile material like a low carbon steel, which will not have a yield point under ordinary rate of strain, will be having yield point. So there are many advantages of HARF processes. So these are applicable for all of them. So high production rates, because the rate of deformation itself is very, very large, and die costs are lower. The finish and tolerances can be easily achieved, and a versatile principle of metal forming, even to form difficult to form metals such as titanium and tungsten alloys, and very minimum or negligible spring back effect, and production cost is relatively lower, and complex shapes, they can be easily obtained in one stroke or one step, okay, and thus eliminate intermediate deformation steps. So it's suitable for a large range of production volumes, such as small numbers, job type production, or medium number of parts made, that is batch size production, or large number of parts made in a given time, or mass production. So for all the three philosophies of production, job type, batch type, and mass production, HARF processes can be easily applied. So these are the advantages. At the same time, it comes with certain limitations. All HARF processes, these advantages and limitations are applicable for all the three types of HARF processes which we would be covering. The limitations are that highly skilled workers are required, and there are the initially very high stresses, high amount of stresses, large amount of stresses are applied, which are the transient stresses, and naturally they are not suitable for brittle materials. They are more likely to crack. And the source of energy, either it is going to be chemical or an explosive or electrical capacitor. Remember that we are talking of energy, large amount of energy, which is going to be applied in a very, very short duration of time. So extra care and precaution has to be taken in designing and operating these systems. And also one can expect proper safety norms laid out by the government authorities are followed while executing these processes. And another is that the dies which are going to be exposed to very high stresses need to be much bigger in section and more rigid, and to avoid the possibility of a cracking. Controlling the application of energy is very critical, as it may crack, as I just mentioned. And also, it's very necessary to know the behavior of the material while designing and operating HARF systems. So after the advantages and limitations, let us look at the applications in general. One major area is shipbuilding industry. Shipbuilding is a major industry where we are required to deform very large parts up to 25 millimeter thick, and over large areas we expect deformation. And it's quite a challenge by conventional means. So HARF or high velocity forming processes are a convenient alternative. And also bending of thick tubes and pipes up to 25 mm thick. The crimping of metal strips. The crimping is the deformation process where two metals are in intimate contact with one another with zigzag surfaces so as to provide interlocking. That's crimping. And another is radar dishes, elliptical domes in space applications, maybe the head of a missile, and the cladding of two different plates, maybe small or large, mainly especially for large. The meaning of cladding is that two metals are cladded or joined so that benefits of both the metals is obtained. One example is a copper bottom steel vessel, stainless steel kitchen appliance or utensil with a copper bottom. So here we use the high thermal conductivity of the copper so as to minimize the wastage of heat. At the same time, we have stainless steel to contain or to have the food, which is a superior material to withstand the corrosion and other chemical attack. So one example is the cladding of stainless steel and copper. Okay, so far we have covered the basic features of HARF processes and also the advantages of all the HARF processes in general, limitations of HARF processes, and also applications. With that, we can go for the first process on HARF principles, which is called explosive forming. As explosive forming sounds, an explosive is used. An explosive is a chemical which can liberate energy, chemical energy at a very, very fast rate due to combustion of the explosive material like TNT, RDX, dynamite, the gunpowder, so on. So many of those, they can be used. And there are many other gaseous mixtures which can be used, but widely used are RDX, TNT, and dynamite. Now, so there are some factors which need to be, we'll come back to this a moment later. So there are various factors which we have to consider while discussing the, or while applying an HARF process for a particular part or a product. First and foremost, it depends on the size of the workpiece. Okay. Then geometry of deformation, behavior of work material under high strain rates, energy requirement and source, cost of die and the tools, the cycle time, and overall capital investment. Eventually, one must remember that economically, the process should be viable or feasible, and above everything, finally, it is the safety considerations. Safety considerations are also very, very important. So while selecting any explosive forming process, we have to consider these factors. Now there are two types of explosive forming processes. The first is unconfined type or standoff technique. Unconfined or standoff technique. Here, standoff refers to the distance between the explosive charge and the work material. Let me refer to this very figure. Yeah, this is unconfined type of explosive forming process. So the word unconfined means not restricted, not contained, not closed, not open. It is open. Okay, it's not restricted. Opposite of this is confined. Unconfined is open. In what way is it open? It is open in the sense that the overall arrangement for executing unconfined type of explosive forming is such that there is water in a huge tank with a very thick wall all around, and within the water we have the work support for the die, and on the die we have the workpiece. So whatever is black rectangle, which you can imagine to be something like this, it may be a plate. It may be a thick plate of around 20 to 25 millimeters, which is very large to deform. It's something like this. In this view, it is appearing as a rectangle. So the black portion is what is the workpiece, and we require proper sealing between the workpiece and the die cavity. This is the die cavity. A simple shape is shown. It can be any complex shape as well, but for the purpose of simple explanation, a simple shape is shown, and the workpiece needs to be very firmly gripped above the die opening, the die cavity, and hold down ring, which is like an arrangement of bolts and nuts over and above. If I show it, hold down ring, maybe it is something like this. So there are a number of bolt holes where you can imagine fixing of this with clamp. In a sense, it is the clamping, firm clamping of the workpiece on the die cavity. The entire arrangement is within water, and leak-proof arrangement between the workpiece and die cavity. So water is all on the outer side, and we have explosive at a certain distance from the workpiece. Now this explosive is at certain distance from the workpiece. This distance between the workpiece and the explosive, this is called standoff distance. So this is what is standoff distance. So this standoff distance is to be decided based on a number of factors. The standoff distance depends on the nature of the work material, the size of the workpiece, and the amount of charge and the finish required, and so on. One very important requirement is the vacuum line or a vacuum pump. This vacuum pump is connected to the die cavity. This space in the die, along which the metal is going to take shape, is to be evacuated. It should not contain air. It should not contain any air. All that air has to be drawn out by a vacuum pump. Just try to guess, why do we require the vacuum line or vacuum pump, or why vacuum is to be maintained? Try to recollect. Some time back, one of the features of HARF processes is requirement of vacuum in the die. Requirement of vacuum in the die, so that there is no adiabatic heating. So that there is no adiabatic heating of the air. And what would happen if we don't have the vacuum line or the vacuum pump? If we don't maintain vacuum here within the die cavity, the rate at which the explosive applies pressure on the workpiece, the rate at which deformation takes place is so large, it is so rapid, okay, about 120 meters per second. At that rate, the air here, if there is any air here, it will go through adiabatic heating, which may lead to overheating of the work material, which may even eventually lead to the melting of the metal. So, to avoid adiabatic heating effects like overheating, damaging the metallurgical properties of the metal, and also to prevent any possible partial melting of the workpiece, we need vacuum. And that makes the process a little more complex, because maintaining vacuum is quite complicated. Okay. So this is the physical typical arrangement available in most of the books. You can go through the books as well. Okay. So to sum up, the tank or the container has thick wall to restrict the shock wave produced by the explosive material. And one thing I didn't mention earlier, the whole arrangement is underground. The whole arrangement is below the ground, so that shock or explosion will not cause any damage to the exterior structures or exterior things. Okay. So the whole thing is below the ground, underground. So below the ground, thick walls of the tank and vacuum line of the die. Die also needs to be very strong. Workpiece needs to be very firmly clamped by hold down ring, and standoff distance, a critical parameter, the distance between the charge or the explosive material and the workpiece, it has to be predetermined looking at various factors. So this is unconfined or standoff type of high energy rate forming or explosive forming process. The working principle is that a gas bubble is formed. A gas bubble is formed the moment explosive is burnt. There is an electric circuit required here, which is there in place, and when the circuit is switched on, then the explosive is detonated, and that produces a shock wave, okay, which is in the form of a bubble, which very rapidly expands and impinges or strikes against the workpiece and instantly deforms the metal at a speed of around 120 meters per second, or approximately 430, around 400 plus, around 400 kilometer per hour speed. So at this speed, there is a likelihood of melting of the workpiece due to adiabatic heating of the air if vacuum is not maintained. So vacuum is very, very critical. It needs to be very much ensure that proper vacuum is maintained. Now looking at the water, why do we use water? What happens if water is not used? Water acts mainly as the medium to transfer energy, and also it ensures that energy is transmitted uniformly. In the absence of water also, explosive forming will take place, but the application of energy will not be very uniform. And another problem along with explosions is a large amount of sound, high intensity sound, which may cause a lot of environmental pollution or disturbance through sound pollution. So there is a requirement of reducing the sound, which is muffling. So water has the role of muffling or reducing the sound. So it helps in uniform transmission of the energy of the shock or the explosion. And one more important function of water is that the application of energy is, apart from being uniform, it is smooth because of water. Application is smooth. In the absence of water, it would be harsh application, which might not provide required finish on the workpiece. So this is what is another issue involved here. So there is a cushioning or a smooth application of energy on the work without direct contact. Now for this process, which is unconfined or standoff technique type of explosive forming process, the process variables are important to be understood well. Okay. The process variables mean here that these factors will decide the technical aspects of the process, or how to go about in applying explosive forming. What are the factors to be discussed? So these are the factors or the process variables, important parameters, you can say, factors or parameters or variables which have to be considered while designing and operating one explosive forming process. It depends on the type and also the amount of explosive. Wide variety is available, one has to select properly. And another important variable is standoff distance. You can just imagine optimum standoff distance is what is important in engineering. Optimum is a very, very important word. Any engineering is centered around optimization. So optimum standoff distance is important. And what happens if the standoff distance is more than optimum? If it is more than optimum, then the application of energy will be not very effective. And as a result, energy could be wasted. All the usable energy due to an explosion may not be used if standoff distance is more than optimum. At the same time, if the standoff distance is less than optimum, if the charge or the explosive is kept very, very close to the workpiece, then the problem is that the initial milliseconds, the application of energy is going to be so large and so high due to transient waves that at certain locations the deformation may be non-uniform. We prefer uniform deformation whenever we are talking of deformation. So if the standoff distance maintained is less than optimum, then there is a problem of non-uniform application of energy, and hence some problem in attaining the required finish and the tolerances. Next process variable important is the medium to be used. Water is used, no doubt, but again it is important. It's an important parameter. What is the water quality and how much of water is there? What is the volume of the tank and so on. The work size of course is important. If the workpiece is very thick and very large, then definitely it would require more amount of explosive and so on. And work material properties are important. If the material is a bit difficult to deform, then extra care has to be taken in ensuring that it doesn't crack or break. And as I have repeatedly mentioned, vacuum in the die is also a very, very important process variable. In the absence of vacuum, there is likelihood of extreme high temperature of the workpiece leading to melting. So these are the process variables involved. Okay, this unconfined or standoff type of explosive forming has these advantages. Let us look at them, try to remember. So there is efficient application of energy of the shock wave through water, okay, and practically it has worked very well. And of course there is less noise because of the fact that it is underwater explosion, and also because of the fact that the entire arrangement, the tank itself is below the ground, so less noise is there. And of course because of the cushioning effect of the water, there is less probability of damage to work, and very large and thick plates can be easily deformed in one step without much of a problem, which would mean a lot by conventional deformation. By conventional deformation, it will be quite a challenge or a task to produce large and thick parts in a single step. So they require a number of intermediate steps which have their own intricacies and difficulties. So eventually, under certain cases, it turns out to be quite economical as well compared to conventional hydraulic press. An unconfined type of explosive forming might end up becoming an economical way of deforming large parts. Of course, it does come with certain limitations. Again, as I mentioned some time back, optimum standoff distance is important. More than optimum standoff distance would mean loss of shock wave energy because of the burning of the explosive. So there is a loss, and required deformation or required shape may not be obtained. Less than optimum, keeping the charge very close to the workpiece, might mean more harsh application of energy of the shock. Also, it might lead to non-uniform application of energy, leading to non-uniform shapes and the tolerances. So optimum is what is very, very important. It has to be decided. One way is empirical. Empirical is past experience. One has to, based on the practical judgment, one has to decide, and based on the practical evidence, one has to decide the optimum standoff distance. Okay. And again, vacuum in industry is expensive to be maintained. Vacuum lines are always expensive because air from all around would try to enter the vacuum space, and atmospheric pressure is enormous and vacuum is expensive. Okay, vacuum is always expensive, hence it adds to the cost. Dies must be larger and thicker to withstand shocks compared to conventional forming. Here the explosion produces very high rate of very high velocity of deformation, as seen earlier in the earlier can say image. 120 meters per second is a very large speed, so you require larger dies, so it adds to the material cost of the die and handling of the die. And with all this, the process is not very suitable for small and the thin workpieces because they are quite likely to be damaged because of explosions. Okay, it's for large workpieces, large and huge, thicker workpieces. And this again, like everywhere else, explosives must be very carefully handled, and all the government rules, regulations regarding handling of the explosives, they must be adhered to without any exception. Again, applications we have seen earlier in general, same, mainly in shipbuilding, making radar discs and elliptical domes and space applications. Example could be the tip or the elliptical dome of maybe a missile or any other space system. So it is about the first variety of HERF process, which is explosive forming, and within explosive forming the first one is unconfined explosive forming. The second is a confined system. It is also called a contact type. It is also called a contact technique type of explosive forming process. And here the principle is somewhat different. Earlier in unconfined type, we have explosive charge at a certain standoff distance from the workpiece underwater. Here there is no water, it's dry. Okay. The principle is that the shock wave or the energy due to the burning of the explosive, a detonation of explosive, is in direct contact with the workpiece. And here again, this process is more suitable for a tubular workpiece, not for thick plates. For thick plates or large plates, earlier unconfined is suitable, whereas for tubes, many tubes which are used in the process industries and also in many other systems, chemical process systems, petroleum complexes for example, you require certain shapes to be given to thick tubes. Under those applications, for those applications, you can imagine application of the confined type of explosive forming process. So in principle, the energy is directly applied on the work without any water medium. There is no water. And as a result of the shock wave or the pressure wave, the tube, usually it is for a tubular, the tube collapses into the die and it assumes the shape of the die. It can be having any shape like bulging or change of shape outside on the outer periphery to make a certain chemical process or a reaction happen or so on. Okay. Bulging is one example and flaring is another. Bulging and flaring. The one which is shown here is bulging. Okay. So the figure here is a simple one which is there in many books. You can refer to the books for more details. Yeah. Here We have a cartridge which contains the explosive material. Again, the explosive material needs to be predetermined with regard to its quantity which is used for a particular process. And the amount of explosive used depends on the work material and so many other parameters. So this is the cartridge, and this whole thing is the die with very thick wall all around to contain or to withstand the shock or the explosion. And this is what is the opening, the hollow opening, and this is the tube. The black is the tube. If I sketch the tube, let me just sketch it for a minute. The workpiece could be like this. Tubular workpiece with quite a thick wall all around, could be like this. So this is the tubular workpiece. So here, this is the die cavity. So as a result of which you can expect bulging of this. This is what is. So there is enlargement. A portion is enlarged in between somewhere. So this is bulging. So whatever was the original tube has now a cross section where it is now bulged. So where to use this is a question actually. These could be the requirements or the needs in a certain chemical industry or a chemical reaction. Okay. So without going into much of the questions like why we need these things, you just can remember that bulging of tubes is one important operation which is required in the petrochemical industry, where there is a lot of work with the pipes or the tubes all around. So this is the workpiece, hollow tube, which is linked to this passage from the explosion. This is the die cavity all around. The die cavity, and again it needs to be evacuated. You require a vacuum line again to prevent the adiabatic heating. And the other end, on one end you have the cartridge with explosive, the other end is closed with a thick plate, very thick plate, and it's not underground because it's not very huge. It's for relatively much smaller workpieces compared to the earlier method of explosive forming, and hence when the explosive is detonated or burnt, the shock wave that is produced will fill all this, or it will pass through all this space and will try to press the tubular workpiece to its end towards the wall of the die cavity. So you can expect that the tube which was straight earlier becomes bulged in the middle portion according to the shape of the die, like this, something like this. It can be an example. Okay, hope you can see this. Okay, I have switched on all the lights, hope you can see. Okay, so there is a bulging in between. So this is confined type, also called contact type of explosive forming, which is in dry state without water. Compared to the earlier method, unconfined type, there is more utilization of the shock wave or the energy of the chemical explosive, as the entire shock wave is contained and there is no loss in water. Whereas the earlier one, there is some loss of shock wave in passing through the water. So this is definitely going to be different on that count. Okay, so entire shock wave front is used. It's more efficient, as I said, because there is no loss in water. And advantages, it is very suitable for smaller jobs. The earlier method, unconfined type, is not suitable for smaller jobs, whereas this is okay for smaller jobs. Disadvantages are that there is a more possibility of failure of a die, hazard of die failure. Again, vacuum is required, and vacuum adds to the cost, as you know. Okay. And again, in the tube, whatever is the air, it is difficult to evacuate that, because for burning of the fuel you require air. So in the tube, whatever is the air which remains apart from the air used for the combustion of the charge, that leads to adiabatic heating, and it has to be taken care of. It is taken care of such that it is within the control, but heating is there. Okay, and it is not suitable for very large and very thick